Hitting the wall. This refers to when a runner or an endurance athlete kind of runs out of energy, runs out of glycogen in their muscles, and it's tough for them to kind of keep going. They have to now rely on using fat for energy, which is a much slower process. So they're probably not going to be able to run as fast or cycle or whatever it is they're doing. And it's really frustrating. And it usually happens in like the really long races, such as the marathon. So let's answer these questions here. Determine his velocity from 0 to 3 minutes. So that's the first third of the graph. So basically, I'm finding the slope of the first section. I'll just highlight A. That's the section, and I got to find the slope of that. So rise over run. The rise looks like, so it's going from negative 1200 up to negative 600. So that's a rise of 600 meters. And the run, it's going from 0 to 3 seconds. So the run is 3 seconds. So the slope is 200 meters per second. And it's asking for the velocity, so I'll give a direction here. Now, if you look at the graph, read the heading, it says the direction is relative to the finish line. So this would be positive 200 meters per second. I'll just say it's going towards the finish line. Okay, so we'll just do the same thing for part B, just for the next segment here, from 3 to 6 seconds. So I find that slope, rise over run. So the rise for that section looks like it's going from negative 600 up to negative 200. So that's a rise of 400 meters. And the run from 3 to 6 seconds, that's a 3-second interval as well. So 400 divided by 3, 133 meters per, not second, minute. Let's make that correction for part A. Meters per minute. Got to read the axis carefully. 200 meters per second makes no sense. That's too fast for a runner. Okay, the third part will be the last 3 seconds there. Same thing. So the slope, the rise for the last part looks, so it's going from negative 200 up to 0, the finish line. So that's a rise of 200 meters. And a run of 3 seconds again. So that would be 66.7 meters per minute. So they're slowing down. They're running out of that glycogen. They are hitting the wall. All right, draw a velocity time graph to match this. Draw a velocity time graph to match this. So, pretty happy that all of these segments on the graph are straight. We're not dealing with any curves here, so that's nice. Okay, so I'll just sketch out some axes. Time in minutes, velocity in meters per minute, with the direction being relative to the finish line, or I'll say towards the finish line. towards finish. And this is just three chunks here. So from 0 to 3 seconds, from 3 to 6 seconds, from 6 to 9 seconds. So I'll just partition my time axis 0, 3, 6, 9. So not seconds, minutes. I keep making that mistake. And then in terms of the velocities, well, the highest velocity I'm going to have to graph is 200. So I'll just put a mark near the top. I'll label it with 200. And then I need to graph 133 and 66. So just estimating, like 100 would be halfway, yada, yada, yada. They look like they're actually evenly spaced, if my mental math is correct. So I'll just say 66.7 and 133. It was kind of a fluke that they were evenly spaced. It wasn't exactly going for that. You don't always draw things evenly spaced. It just happened to be that that's how the numbers worked out. 66.7 times 2 gives me 133. 66.7 times 3 gives me 200 exactly. So this kind of was a fluke for this one. Okay, so for the first 3 seconds, it's 200 meters constant. So that's a horizontal line at 200. And then from 3 to 6 seconds, it's 133 meters per minute constant. So another horizontal line. And then from 6 to 9 minutes, it's 66.7 meters per minute constant. So that's what the graph looks like. There's no need to try to make those lines connect with each other. Yeah, that's it. Okay. E. If he were able to maintain his pace from part A for the remainder of the race, how much better would his final time be? So can do that in 2 ways, actually. Algebraically, we can do it. But I'm going to be a bit lazier. Well, not lazier. Maybe a bit less accurate, but also quicker. And I think this is a cooler way to do it as well. If I can find my draw line. Is there a draw line? Here we go. Draw a line. If he was going to maintain the pace from the first 3 seconds, well, then that straight line segment for those first 3 segments would just continue with the same slope. So if I start at negative 1200, okay, now I want the draw line function. Let's try that again. There we go. So if I just follow the same slope until it hits the time axis, it's not the most accurate. I can see with my eyes that my yellow line is not exactly the same slope as the beginning blue line, but it's pretty close. And it's leading me to 6. It's leading me to 6 minutes. So if he was able to maintain that pace, he would have finished 3 minutes earlier. Approximately. You could do the algebra if you want to like get a more precise answer. That involves a bunch of steps though. yeah, the steps would have been find out how much distance they had left after 3 seconds, and then divide that distance by the 200 meters per minute. And actually, that does give you 3. The algebra does give you 3 minutes exactly as well. All right, so that's part E. And then finally F. What was his average velocity for these final 9 minutes? So he was a bit faster, and then he slowed down, and then slowed down again. But what if we're asking about the average for the whole thing? Then I'll say average velocity. Then if we want the average for the whole thing, then we take the displacement for the whole thing, and we divide it by the time for the whole thing. So the displacement for the whole thing, looking on the graph, it actually ends up being from negative 1200 all the way to 0. So that's a rise, a total rise of 1200 meters. And the whole thing took 9 minutes. So that would be the run. So essentially what I did was I found a slope of what we call a secant line. So if I start at the very beginning and draw a straight line to the very end, this is called a secant line. And you just join any 2 points of a graph. And that's actually how you calculate the average velocity. Or you can just use the formula like I did. So 1200 divided by 9, 1, 3, 3.3 repeated, I think, meters per minute. So again, that's mental math. There might be a mistake there. I'm not worried about making perfect videos. I apologize if that's what you want, but I don't have that much time. Okay, so meters per minute toward the finish line. All right, so that's hitting the wall.